Traditional automotive engineering is built on a specific bedrock. If a system has zero hardware faults and the code executes as written, the system is safe. Artificial intelligence introduces a paradox into this logic. A perception model can execute perfectly, yet still initiate a maneuver that leads to a collision. These failures are often triggered by out-of-distribution data. When the operating environment diverges from the training data, the model can make incorrect predictions with high statistical confidence. To manage these risks, the industry is adopting the ISO PAS 8800 framework. This framework replaces the concept of static post-market safety with an active runtime data lifecycle. Consider an autonomous emergency braking system. For years, its neural network was trained on high-resolution data captured exclusively on clear, summer city streets. That vehicle is now operating in a severe winter blizzard in a mountainous region where visibility is significantly obscured. Verifying the software binary is no longer enough. Safety now requires the system to account for the shifting reality of the outside world. System degradation in the field manifests as a mathematical divergence, categorized into three specific types of drift. Covariate shift alters input features, shifting the bell curve as pixel data diverges. Label shift tracks class frequency, where sudden pedestrian spikes alter prior probabilities. Concept shift is most severe. Underlying physical laws change, requiring a different output for the exact same input. We can apply this framework to diagnose the braking system failure in the snowstorm. Heavy winter clothing, hoods, and deep snow obscure the articulated joint structures the model usually uses to identify humans. Because the physical definition of a pedestrian remains constant, we can rule out concept shift. The issue is covariate shift. The pixel distributions and edge contrasts the model relies on have morphed into patterns it hasn't seen before. The model is now attempting to infer bounding boxes across a low-density, unseen region of its original training parameters. Without a way to mathematically quantify this divergence in real time, the system will remain dangerously blind to the obstacles ahead. ISO PAS 8800 mandates that safety monitoring move from passive observation to active onboard quantification. The industry standard metric for this runtime evaluation is the Population Stability Index, or PSI. PSI compares summer training distributions against incoming winter field data. A score under 0.1 is stable. Over 0.25 indicates severe drift. In the blizzard, the calculation ticks up to 0.32, plunging the system deep inside the critical red zone. The vehicle also monitors for anomalies within individual frames. This involves analyzing the model's final output layer, specifically looking for drops in Softmax confidence scores. As the PSI spikes, the model's internal confidence for pedestrian detection drops from a baseline of 0.85 down to an unreliable 0.42. The system is now mathematically aware that its understanding of the world is insufficient. At this point, the vehicle executes an architectural failsafe, using abstention mechanisms to avoid making a low-confidence guess. With the failure identified, the vehicle moves to extract the specific data required to close the performance gap. Streaming continuous sensor data from thousands of vehicles to the cloud is impossible due to bandwidth constraints. ISO PAS 8800, Clause 14.7, provides a solution through purpose-based field data collection, capturing data only when safety-critical logic gates are triggered. These logic gates monitor for performance triggers. The most critical trigger is the plausibility violation. This occurs when the AI's output contradicts physical laws, like detecting an object moving faster than any possible human speed. In the blizzard scenario, the bounding box hallucinates, jumping instantaneously across the frame, registering a pedestrian moving at 100 kilometers per hour. When this violation occurs alongside a high PSI score, the vehicle's recording buffer locks. The system isolates a high-resolution, 10-second window directly surrounding the anomaly. By ignoring normal driving and capturing only explicit logic violations, the system extracts the exact data the neural network needs to study. This data must be transmitted back to the manufacturer without being intercepted or corrupted. The data packet is assigned a SHA-256 hash and signed within the vehicle's trusted execution environment. It is then sent to the cloud via TLS encryption to prevent tampering. Once in the cloud, the data is manually labeled and injected into a retraining loop. Engineers use domain adaptation to integrate the new information. This process blends the winter data distribution back into the summer baseline, creating a unified model. This forces the model to reconcile different features, teaching it to recognize pedestrians regardless of the weather. This updated winter-hardened model is then pushed back to the global fleet via an over-the-air firmware update. ISO PAS 8800 treats machine learning models as evolving components rather than static software binaries frozen in time. An autonomous system requires an architecture of constant feedback. Its safety depends on a continuous cycle of detection, extraction, and adaptation.